All right, so now we're going to look at various charges and conductors and capacitors here. So, in general, electrons are much smaller than protons, if you learned that in your chemistry class. And so, negative charges are generally what moves. Um, might be strange, but that is what happens. So what we want to know is talk about how charges move. Charges can move, and for a lot of objects, there's either friction or contact, so the charges can physically transport from one object to another. The electrons can move, or there's something called induction, which allows us for polarization. That is to say, if you bring a positively charged object near another object that maybe doesn't have positive charges, the electrons on here are going to move in such a way as to be drawn towards here. And any positive charges will kind of separate, right? Or in the case that electrons are things that move, the electrons that were over here come to this side, and that leaves behind positive charges who really can't move because they're pretty big. So that ends up creating a charge separation, which we call a polarization. But electrons are the main way that they flow. On conductors, electrons can flow easy across objects, but on insulators, charges have a hard time moving. They can move a little bit, but not nearly as easily on conductors. Conductors, electrons are free. They're unbound to any particular atom or bond, and so they're free to move around, and that's what gives metals a lot of their properties. There's a thing about grounding. If it is grounded, electrons can flow to and from ground very easily, and that can give an object extra charge onto it. Okay, electrostatic condition is usually what happens in a conductor. It happens in most cases except for when you're putting it under an electric field like in a circuit. But on most cases when we're doing these kinds of problems, the electrons are free to move around. They will move in such a way to balance any external charges. So what they'll do is, see, the thing is, the electric field inside will be zero in a conductor. Why will it be zero? Is because if there was an electric field, let's say there was an electric field, then the electrons are going to move. So let's say you have an electric field here, then any electron that was over here is going to feel the need to then move up to here because the negative charges are going to oppose the electric field or go against, they're going to feel a force opposite the direction of the electric field. So then the negative charge is going to be over here, and that's going to weaken the total electric field because this negative charge creates an electric field in itself going this way. And so eventually what ends up happening is the charges are going to settle to where there's no net force on the electrons in there, and that means the electric field goes to zero. Everywhere along a conductor, the electric potential is the same for that reason, along the surface of the conductor, because the electric field ends up going to zero. At the surface, the electric field ends up being perpendicular. So we say everywhere along the wire or the conductor, the potential is the same. So when two conductors touch, the charges are going to redistribute, so the electric potential is the same everywhere on those two conductors. And the electric field is perpendicular surface of a conductor because the surface is equipotential, right? So if this is an equipotential part from here to here, then that means the electric field line has to be perpendicular to that. A lot of times we can use Gauss's law to determine how much charge is on the various surfaces of a conductor because you know the electric field is in here. So if your Gaussian surface goes through the interior of a conductor, then you know the flux is going to be zero. When charges are surrounded by a conductor, it's fair to treat. So let's say I have a whole bunch of point charges over here. This is another fact. It's fair to treat all of these point charges as a single charge. If you're surrounding a conductor, this is like a metal conductor, then you can treat all these charges interior as a single point charge with the total charge there for the purposes of force and potential. And it's kind of an interesting fact about conductors that they can do that shielding, and it's a consequence of the fact that they will rebalance their charges in order to make the electric field zero. Capacitors, most commonly parallel plate capacitors, but just basically in general is whenever you have capacitors, you're having a potential difference between them. Okay, so there's a potential difference between here, which means there ends up being this electric field, like this area might have a bunch of positive charges. This thing might have a bunch of negative charges. And remember that in a capacitor like this, the electric field is going to go from positive to negative, and it's going to be uniform through there. So they create an electric field due to the charge distribution. Q equals CV is the relationship between the charge and the potential difference here. right? So you have a potential difference here. You might have amount of charge causing that potential difference, right? And so Q equals CV is the relationship there. The total energy stored in a capacitor can be given by 1/2 CV squared or 1/2 QV, and you can derive each of these equations from the other one by using Q equals CV. For a parallel plate capacitor, the electric field is mostly uniform. It's less uniform near the edges, but it's mostly uniform here. Around the edges, it can do things. We call this fringing fields. These are non-ideal, and we don't usually model them. But for a kind of a big plate that's very large and very wide compared to how thick it is, then we assume the electric field in the interior of the capacitor is pretty uniform. The capacitance is given by epsilon naught times the area of the plates divided by the distance, which is the physical separation between the plates. And the electric field is going to be the voltage divided by the distance. And this one's pretty easy to derive because remember that the electric field is negative dV dx, and the potential drop is sort of constant. So, and the electric field is uniform, so this ends up being negative change in voltage over the distance here. And the negative, this is just telling you the magnitude, really. The negative just sort of indicates the direction, right? So important problem solving steps when, this is going to come out more when we do more circuit analysis, but when connected to a voltage source, the voltage is kept constant, right? That means when you do your Q equals CV and you do any modifications to the capacitor, the voltage is kept constant. Whereas when the capacitor is isolated, the charge is kept constant. That means the Q is constant, because if you isolated it from anything else, then the charges are sort of trapped onto those conductors there. Okay, dielectric is if I insert something. So if I have a parallel plate here and I insert a material in between them, so I insert like a block of like glass or some other material in here, you are going to increase the capacitance. And the capacitance increases by the dielectric constant we call kappa. This is technically kappa, not a K, but it looks very much like a K. Kappa is our dielectric constant. What it ends up doing is the dielectric constant increases the capacitance. So if Q equals CV, it kind of depends on what's changing, but assuming that you leave the charge the same, let's say we isolate it so it's the same charge. What happens is when you insert the dielectric constant, the capacitance goes down and the electric potential is then going to go, the voltage is going to go up. Now, if you, however, keep the voltage the same, well, actually, so let's talk about that. So the Q is going to, this stays constant in this scenario. The capacitance doesn't go down. Capacitance increases. So I put in a dielectric, so the capacitance goes up, the potential goes down, but the electric field is still the voltage divided by the distance. So what ends up happening, and if you don't change the geometry, you don't change the separation, is when you insert the dielectric, the voltage goes down, if you assume the charge is constant, and the electric field will then have to go down as well. So this results in a lower potential difference for the same charge on the capacitor, or for the same charge, a lower potential. And a lower potential means a lower electric field, okay? The dielectric constant is just whatever is a property of the material itself. It's a property of what the dielectric is made up of, okay? So let's go look through some examples of some problems that we go through here on this topic. So we have a parallel plate capacitor consists of two large conducting plates, area A. So the area of this is A, separated by a small distance D. The capacitor is initially connected to a battery and fully charging the plate, so the top plates hold a positive charge plus Q, and the bottom plates hold a charge negative Q. The battery is then disconnected. So then a dielectric is inserted to completely fill the space between the plates. So we're going to derive an expression for the initial capacitance of the capacitor before the dielectric. So this is just knowing your formula, epsilon naught A over D. It's not much of a derivation, but just wanting you to have a good starting point. What is the energy stored in the capacitor, right? So that's 1/2 CV squared, but we don't know what that is. We don't know what the voltage is, but we know Q equals CV. So then we can solve for the voltage, Q over C, based on, because we know what the capacitance is, or we've derived it from here, and we know the charge, so we can plug that into here. And you get 1/2 C times Q squared over C squared, because you got to square it. That will cancel one of those. And that's 1/2 Q squared divided by C. But we can't put our terms in terms of C. We got to put our answer in terms of this thing. So it's dividing by this thing is multiplying by the reciprocal, right? That's how fractions work. So like that. Derive an expression for the electric field between the parallel plates. So the electric field is going to be the voltage divided by the distance for the parallel plates. I don't know what the voltage is, right? So voltage is Q over C times D, right? So you can do that. Q over C times D. We know the capacitance is epsilon naught A over D times D, and you can see the D cancels, and that's why we get the Q over epsilon naught A. Sometimes people use the Q over A as the, you can see this sigma just as a note. This can be the Q over A. This is the charge per area. Charge per area. This is going to be charge density. Density per area. So you might see that formula show up some places if you've been taught this. Okay, so after the battery's disconnected, so disconnected means the charge is constant at this point, right? A dielectric is inserted, determine expressions for the following values. So the new capacitance is kappa epsilon naught A over D, okay? So that's our new capacitance. The potential difference is still, let's see, we could do Q equals CV still, but remember now the charge is constant during this time, so this still remains the same, so it's still Q divided by the capacitance, but it's now Q, there's a kappa in here, kappa epsilon naught A over D, and so what you can see is if you multiply by the reciprocal, QD over kappa epsilon naught A, and if you compare that to the potential difference here, you see you've divided the potential difference by kappa, but that makes sense because the Q is kept constant. How much work did it take to put the dielectric between the plates? So if you think work is the change in energy. So if I do work on it, I'm going to change the energy. That work that I did to put that thing there would have caused an increase in the potential energy. So we're going to talk about the change in the potential energy. We know how much potential energy we started with, which was this. So we need to talk about what the potential is at this point. It's 1/2 CV squared, right? But you can use this C and this V squared if you want. Or you can do it in terms of charge. I think we did it in terms of charge before. Q over epsilon naught, or 1/2 Q squared over that. Actually, it's fine. So do 1/2. The C is as the kappa epsilon naught A over D. And then the potential here is this thing here, QD over kappa epsilon naught A. And if you square it, you're gonna cancel these, and these aren't going to be squared. You're going to square that, and you're going to cancel that, so that's not going to be squared. So it's going to be 1/2 Q squared D over kappa epsilon naught A. Okay? So that's the final energy. So the change in potential energy is going to be the difference here. Q squared D over kappa epsilon naught A minus the amount of energy we had before, which was 1/2 Q squared D over epsilon naught A. Right, and if you want to just to simplify, you can factor out the Q squared, the D, the epsilon naught A, and you get 1 over kappa minus 1. Because kappa is bigger than 1, what's going to happen is going to be less energy, so you're going to lose some. I mean, it didn't take any energy, it took negative amount of work to put the dielectric between the plates, right? Okay, so let's find the new electric field between the plates. The electric field is the voltage divided by the distance, but now the voltage was divided by kappa, right? So the voltage here was QD over kappa epsilon naught A divided by the distance. That will cancel. So you get Q over kappa epsilon naught A, and this is what you see is the electric field decreased, right? So that's just a manipulating of those few equations that we're just doing for something like that. Now, suppose instead the dielectric is inserted while the capacitor remains connected to the battery. So now the voltage is constant. Determine the expressions for the following values. Express your answers in terms of all of these things. What's the potential difference now? Well, originally, if we look at the original scenario, Q was equal to C times V, right? So now this part is constant, and now the charge might change, right? So we want to think about what the potential is across the plates. So it's going to be the same as it was before. So it's just going to be Q over C. So this part isn't changing, right? So you can just put it in terms of Q over C. And Q is over whatever the new capacitance is, kappa epsilon naught A over D. And that's going to be QD over kappa epsilon naught A. Actually, we can't use this because, oh yeah. So the potential is the same as it was before. This is before I put the dielectric in. That was the potential, and now still the same potential difference. Okay. Now when I do 1/2 CV squared, okay, it's 1/2 kappa epsilon naught A over D, but the voltage didn't change. It's still this thing here. So it's QD over kappa epsilon naught. Actually, this one we don't have the kappa in it, because this is the potential before I added the dielectric, right? And it's still the same afterwards. Kappa epsilon naught A over D squared. So what happens here is when I square the D, one of them will go away. One of those will go away. So you have 1/2 kappa Q squared D. Q squared D, yeah. And that would be the energy. And so you can see the energy is going to increase now, right? Because the kappa doesn't cancel, because the potential, like this is before I put the dielectric in, this was the potential. Now it's still the same because I've connected to the same battery. The amount of energy stored on the plates, the amount of charge stored on the plates is Q equals CV. Now that I know the new kappa, epsilon naught A over D, and then I know the original voltage, which was QD over epsilon naught A, you can see this is going to cancel, and you get kappa times Q. Now that's the new charge, and that should make sense to you, because if the voltage is constant and I increase the capacitance by kappa, then the Q is going to go up by kappa as well. Okay, so those are kind of the two different configurations, whether or not the capacitor is connected to a voltage source, and so the voltage remains constant, or whether or not the charge remains constant. All right, let's take a look at some charging mechanism question here. So we have two isolated uncharged conducting spheres located distance of d apart. Sphere A has a radius RA, and sphere B has a radius RB with RA bigger than RB, as you can see in the picture. Sphere A is given a net charge of plus Q, while sphere B remains uncharged and isolated. The spheres are held in place and do not touch. Draw on the spheres how the charges will be distributed on the spheres, including the total charge on this sphere. So what's going to happen is we have this positive charge, so a lot more of the negative charges over here are going to be attracted, and then that will leave some devoid positive. But you want to keep it balanced, right? So if I draw 3 over here, net charge 0. It's not that the charges got away or anything. It's just simply that the charges are separating here. That means the more of the positive charges are going to be on this side, and this one has a net positive charge, so you can leave them. You don't have to have 3. It's just sort of illustrating. There's going to be positive charges. They're going to be over here. Now, you can put negative charges here if you want, but you need to put fewer of them if you do, because ultimately this thing has a net positive charge here. So generally, if it's a net positive, I just include the excess charges there. So that's kind of what's going to happen there. Indicate without calculation whether the electric potential B is positive, negative, or 0 after sphere A is charged. Justify your answer. On the surface of the sphere, right? So remember, everywhere in a conductor, on the surface of a conductor, the potential on the surface, on the surface of it, the sphere, on the surface, it actually should be 0. Why is it going to be 0? First off, it's an equipotential surface. So everywhere on the surface, same potential, right? That's always true about a conductor in electrostatic conditions. The other part is we think about what is the KQ over R. Okay, that is the electric potential, right? And so you think of it like a point charge, but like because it's a conductor and it's shielded like that, we can treat like all the charges interior as though it were a point charge. So the enclosed charge in here, the amount of charge contained on the sphere is still 0. So this is still 0 volts on that potential. Okay, now a thin conducting wire connects the two spheres momentarily. After equilibrium is reached, the wire is removed. Okay, derive an expression relating the final charges of QA and QB on each sphere after the connection, using the fact that the connected conductors must be of the same electric potential. Oh, I wasn't supposed to write that. Okay, so we're connecting this with the wire, and now we have to say there's two things that have to be true. One, the total charge has to remain the same. Okay, so whatever QA plus QB is, whatever their new charge separation, has to still equal Q, because I can't just create charge. The charge has to come from somewhere. So the total charge has to be the same. And now the potentials have to be the same. And on the surface of the potentials, you just do KQA over its distance that's the radius, it has to equal the potential on this surface here, which is KQB divided by RB. Okay, so then we can cancel out the K's, and we want to solve for the final charges QA and QB. We have a systems of equations. You're going to have RBQA is equal to RAQB by just cross multiplying. And then you can solve for it however you want. You could solve for QA if you want. It's Q minus QB. And you're going to plug that into there. So you get RB times Q minus QB is equal to RA times QB. And so you can distribute. You'd be RBQ minus RBQB equals RAQB. You can add them together. RBQ is going to be QB times RA and add RB. You just factor that, and then you can divide that over. So QB is going to be RBQB over RA plus RB, like that. And then and then you can do Q minus that. So you could do QA is going to be Q minus QB now. Or you could do this one. QA is RA over RB. That might be easier. RA over RB times QB. And that RB is going to cancel with that one. So you get RA on the top instead. Okay. Over RA plus RB. Like that. Okay, so that's going to be the two charges there. Determine which sphere ends up with the greater charge magnitude. Justify your answer. So who's going to have greater charge? It's going to be the bigger one, right? Because they have the same potential. So whoever has the bigger radius is going to have the bigger amount of charge. So because they have the same potential. So charge A, because RA is greater than RB, for QA over RA to equal QB over RB, the charge on A has to be greater. And you can also do this analytically because they both have the same denominator. RA is greater than RB. So and they're both sorry, this is not supposed to be QB. I don't know why. This is Q. Yeah, this is supposed to be Q. My bad. Because I was supposed to divide that over. Yeah, they have the same total charge, but RA is bigger than RB, right? So then the QA is going to be bigger. That's another way to argue that one. So instead of connecting the spheres to each other, suppose sphere B is grounded. Okay, so B is grounded here while sphere A remains isolated and charged to plus Q. After the system reaches electrostatic equilibrium, the ground connection is removed. So what's going to happen here is, because this is positive charge, this guy's going to have some negative charges now come from the ground. And then before you remove this charge, this is like induction where the negative charges are drawn to this guy, right? We're going to disconnect this now. So now sphere B has a net negative charge because the excess electrons from ground flow onto sphere B. So then after the ground connection is removed, does sphere B exert an attractive or repulsive force on sphere A? Well, this thing's positively charged, this is negatively charged. It's going to be an attractive force because they're opposite charges. And that's pretty easy to answer on that one there. Okay. This one's kind of an interesting problem. I modified a past FRQ because a lot of the times we can use a combination of Gauss's law with charge and voltage to create the capacitance. So this is an interesting problem where we're going to talk about that. So I have two spherical conducting shells centered on the same point, forming a spherical capacitor. The inner shell is a radius r and carries a charge of plus Q. The outer shell is a radius 4r, carries a charge minus Q. The space between the shells is a vacuum. Express all algebraic answers in terms of Q, big R, Q. There's no little r. Sorry, this is a mistake. Q, R, and fundamental constants. Derive an expression for the electric field between the two regions here and here. So what we want to do is we're going to create a Gaussian surface here because the electric field's radially, right, outward because it's spherical, right? So that's why our Gaussian surface is going to have an electric field going in this direction, right? So that electric field, that Gauss's law, so the integral of E dA, the electric flux, is the enclosed charge over epsilon naught. So that's going to be the electric field times the surface area of our Gaussian surface. That's 4 pi r squared is equal to the charged enclosed, which is just Q over epsilon naught. So the electric field is Q over 4 pi squared epsilon naught. Okay, so that's the electric field there. Now we want to find what is the potential difference between the inner and the outer shell. So we're going to, if we want the change in potential related to the integrals, in this integral here. Now the negative, whether it's positive or negative doesn't really matter. You just got to remember that the positive charge is at a higher potential than the negative charge. So I usually don't really worry about the negative sign, but I know some of you will worry about that. Now we know the function of the electric field. It's Q over 4 pi r squared epsilon naught. And we're going to integrate this over dr because we're going to just take a straight line path from one surface to the other. And we're going to integrate it from r to 4r. We can't start at 0 because we're starting from the outer edge of that conductor, right? So r to 4r. Now this is going to be integral of, you can bring out the q, negative q over 4 pi epsilon naught, and you're really just doing the integral of r to the negative 2 dr. And so power rule will tell you it's r to the negative 1 over negative 1 from r to 4r. Those negatives cancel. And so this gives q over 4 pi epsilon naught. And you would make this 1 over 4r minus 1 over r. You can factor out the r. And this becomes 1/4 minus 1, which is negative 3/4. And so I don't really care about the negative sign. I just care about the total amount. It's going to be 3/16 q over pi epsilon naught. That is the potential difference here. Okay, and then now we want an expression for the capacitance of the capacitor here, right? So that capacitance is Q over, capacitance is C is equal to QV. Sorry. Q is equal to CV, so the capacitance is Q divided by the potential difference. So we're going to divide that over and bring that up. So it's going to be 16 pi epsilon naught over 3, like that. Sorry, I left out the R. There should have been an R here. I felt like there was something missing. So I missed the R in here because I factored that out, but I forgot to say I did. So then that is going to be, so this is the expression for our potential difference, right? And then this is our expression for the capacitance. It's going to be 16 pi epsilon naught R over 3. And that's that. So that's kind of an interesting way to calculate the capacitance. It's very common to just use Gauss's law to find the electric field. And then from the electric field, we can take the potential difference, and it's going to be based on the charge. And that ratio, you see, is independent of the amount of charge. And so it's a property of the shape of the spheres and the size of them.